Hironori Matsumoto, from Osaka University. He's going to talk about the XRISM observatory and the result. Basically he graduated the University of Kyoto, and after that he went to
After Kyoto, Riken
as a postdoc. Then he went to the MIT for the as a postdoc. And at that time, I was the postdoc at CFA, and we meet together and start collaboration, especially for the ultra-luminous X-ray sources, especially in MED2. And we wrote 3 papers in early 2000. Around 2020, already 25 years ago.
20 years ago.
Quarter decade, quarter century ago. And I wrote the first author is the radio part, about 70 plus citation. He wrote the X-ray Chandra, first Chandra result, right?
Right.
So that he got 200 plus citation, and our theory member, Ebisu-san, his first paper got the 300 citations, so 3 papers, pretty good. I'm the worst citation, but well, we got the pretty good results. And then after that, he moved to the Kyoto University as the assistant professor, and moved to Nagoya University as the associate professor, and now he's the full professor at the Osaka University. So today he's going to talk about this one, so let's welcome our speaker.
Thank you very much. Thank you very much. First of all, I want to thank you all for giving me this great opportunity to talk about the XRISM results. And my goal of this talk is let you know what XRISM can do. And I would be happy if you become interested in XRISM and would like to propose some observations for XRISM project. That is my pleasure. Okay, first, let me introduce the XRISM project, XRISM satellite. XRISM is X-ray Imaging and Spectroscopy Mission. And this satellite has 2 X-ray mirrors, which are called XMA, X-ray Mirror Assembly. And the other detectors, there are 2 kinds of detectors. One is X-ray CCD. This is X-ray CCD is a typical detector in X-ray astronomy. And the other one is, this is a special type detector, X-ray microcalorimeter, which is called Resolve. And what is super about XRISM? They are very important, so please remember these 2 things from my talk. Okay, one is the energy resolution above 2 keV. And this is brought by Resolve, X-ray microcalorimeter. And one more special thing is this detector is working even for spatially extended objects. Before XRISM, we have used gratings to do precise spectroscopy, but this is a non-dispersive type detector. So using gratings, we cannot do spectroscopy for spatially extended object, but XRISM can do for spatially extended object. The other special point is wide field of view. This is brought by X-ray CCD, which is called Xtend, and the field of view is larger than full moon. And this is a picture of X-ray mirror, and it is a Walter 1 type X-ray mirror, and it has 200 shells. So this mirror has a large collecting area, effective area, but it is very light, 40 kilograms or so. And unfortunately, the spatial resolution is not so good. It has a moderate energy spatial resolution, about 1.5 arc-minute. This is a picture of X-ray microcalorimeter, which is called Resolve. And this is a picture of the sensor. It has 6 times 6 pixels, and the field of view is about 3 arc-minute. And 1 pixel size is 30 arc seconds times 30 arc seconds. And the sensor is put into a dual. How to measure X-ray energy of X-ray photon? This is the principle. The absorber absorbs the incoming X-ray photon. And then the temperature of this absorber will rise slightly. This is a picture of the temperature of absorbers. This is time, and this is temperature, and this time shows when the X-ray photon absorbs this absorber. And the temperature is getting high a little bit, and we can measure this temperature rise. And this temperature increase is proportional to X-ray photon energy. So we can measure the X-ray photon energy, and it has very good energy resolution of about 5 electron volts. And as I said, this is non-dispersive type instrument. It is effective for spatially extended object. And this is a typical example of X-ray spectrum obtained by Resolve. This axis shows X-ray energy, and this axis shows counting rate. And we can obtain X-ray spectrum shown in black line with X-ray microcalorimeter. And also we have X-ray CCD Xtend. We can obtain the spectrum like this. And this spectrum is from Perseus clusters of galaxies, and please take a look at here. And with X-ray CCD, there is only a bump-like structure like here. But with XRISM, we can resolve this structure into several lines. They are fine structures of characteristic X-rays from iron 24+. This means helium-like ion of iron. And so we can observe fine structures, and by using fine structures, we can do plasma diagnostics to infer the temperature or density or blah, blah, blah. And of course, if we measure the center energy of these lines, we can measure the Doppler shift of celestial objects. This axis shows the X-ray energy, and this axis shows resolving power, E over delta E. And this line shows the resolving power of XRISM, and other lines shows other instruments, mainly gratings on board other satellites, other X-ray astronomy satellites. And as you can see, above 2 keV, XRISM has the largest resolving power. And yeah, this. But unfortunately, there is only one problem about a microcalorimeter. That is a gate valve issue. What is a gate valve? Gate valve is attached on top of the dual. This is closed on ground in order to keep the inside of the dual vacuum. And the gate valve should be opened after the launch in space. But unfortunately, the gate valve did not open in space after the launch. But this gate valve has a window of beryllium. The thickness is 270 micrometer. So this window is transparent X-rays above 2 keV. Unfortunately, X-rays below 2 keV is absorbed perfectly with this window. So with this gate valve issue, this axis shows X-ray energy, and this axis shows effective area. And if the window opened, we would have the effective area is like this, showing in black line. But the gate valve did not open, so the effective area reduced to this level, shown in red line. This figure also shows the effective area, but in logarithmic scale. And this figure, there are effective area of other gratings. And here is a resolve with gate valve closed. And you can see above 3 kb or above 4 kb, still resolve has the largest effective area. So this means resolve is very good, above 2 kb in energy resolution and effective area, good sensitivity. This is the other detector, X-ray CCD. Actually, my group, Osaka University group, has contributed a lot to, for the development of this sensor. And this is a picture of a flight model of X-ray CCD. And these fingers are mine. I'm doing some experiments for X-ray CCDs. And one special point about this X-ray CCD is large field of view. And this is a picture of X-ray galaxy clusters. And this is the field of view of XRISM. And you can barely see the field of view of other missions. Here is Chandra, and here is Suzaku, and here is Asuka, blah, blah, blah. And as you can see, the Xtend has the largest field of view. The size is about 40 arc minute times 40 arc minute. And X-ray CCD have a moderate energy resolution. And this is X-rays from Abel 2319, the class of galaxies. And we can see the helium-like characteristic X-rays here. Of course, we cannot observe the fine structures of this line, but we can observe the helium-like characteristic X-rays like this. And this panel shows the grasp. What is grasp? Grasp is effective area times the field of view. This is a measure of sensitivity for spatially extended object. And you can see the XRISM Xtend X-ray CCD has the largest grasp compared with other X-ray missions. So this means X-ray CCD on board XRISM has the largest sensitivity, highest sensitivity for spatially extended diffuse object. And this is a history of our sad history about microcalorimeter missions in Japan. The first trial was 2000 when I met Satoki, maybe around this time. We tried ASIAA, but unfortunately the launch was failed. And our second trial is Suzaku mission in 2005. It was launched successfully, but the microcalorimeter did not work in space. The third trial is Hitomi, which was launched in 2016. It was launched successfully, but unfortunately, the satellite communication was lost just 1 month after the launch. So only a few objects were observed with the microcalorimeter on board the Hitomi satellite. And we launched XRISM satellite in 2023 and launched successfully, and the instruments are working well. Of course, although we have a gate valve issue for microcalorimeter, but before XRISM, we tried 3 calorimeter missions, and finally, our dream comes true. So this is basic knowledge about XRISM. Do you have any questions about XRISM projects? Okay.
Do you have any comment about the lifetime of this microcalorimeter?
At least 3 years. But the calorimeter is using the liquid helium. But after the evaporation of helium, we can still observe using the refrigerator. So we expect X-ray microcalorimeter will continue, can observe for more than 5 years, maybe 10 years, we expect.
It's less sensitive?
Yes, almost the same sensitivity.
Same sensitivity, even though without coolant?
No. Yes, almost the same level.
Then why did you?
Once the detector cooled to 50 millikelvin using helium, after that, we can keep the temperature with refrigerator. But to cool down the detector to 50 millikelvin, we need liquid helium. Okay, let's move on to the scientific results. Already some papers have published. These are the list of the published results, and including one Nature paper here, and some of you may know about them. And we will have past J special issue for XRISM. This includes many scientific results. Some of them are already published in arXiv, so you can see them in arXiv. And the instrument description papers will be included in this special issue. So stay tuned. Maybe this special issue will come out in this summer. So I want to introduce all of these results, but unfortunately time is limited. So I select two topics from this list. One is a Centaurus cluster, which is of course our first Nature paper, so I must explain it. And the other one is Sagittarius A East, supernova remnant. And if time is allowed, I will introduce the third result of the quasar, PDS 456. Okay, let's move on to the first result. This is a result about Centaurus galaxy cluster. What is clusters of galaxies? You are familiar with that, of course, I think. But this picture shows X-ray image of Perseus clusters of galaxies. And this picture shows the optical image. And we can see many galaxies in optical band. So this is called cluster of galaxies. But in X-ray band, X-ray emitting hot gas, we can see X-ray emitting hot gas filling the entire volume of the cluster. The temperature of the hot gas is about a few kilo electron volts, and the mass of the hot gas is larger than the mass of the total mass of galaxies. So as a baryonic component, the main component is hot gas, not galaxies. Of course, as a gravitational potential, so the most main component is dark matter, and the mass of the dark matter is about 10 times larger than the mass of the hot gas. But as a baryonic matter, the hot gas is the main component of cluster of galaxies. There is a famous problem of cooling flow problem for the cluster gas. What is a cooling flow? At the central region of some clusters, the cooling time of hot gas is less than the age of the cluster. So the hot gas at the center of some clusters must cool down. Then the pressure decreases, and the hot gas must flow into the central region of the cluster. This is called cooling flow. But we have never observed such cool gas at the central region of the clusters. Why? This is called a cooling flow problem. So some energy source must exist at the central region of the cluster to suppress the cooling flow. What energy sources would compensate for the gas cooling? One of the possibilities is AGN feedback. Probably you know about that. AGN have jet, wind, or strong radiation. Then AGN can feed energy to the surrounding hot gas. And this is called AGN feedback. And this process is maybe related to the galaxy black hole coevolution. So many researchers is doing research about this AGN feedback. But the Hitomi observed Perseus cluster in 2016, and Hitomi results suggest that the feedback of AGN is not strong enough to suppress the cooling flow, at least in the center of the Perseus cluster. So what is happening at the central region of the cluster? We don't know yet. So we observed another cluster of galaxies, Centaurus cluster. This is a Chandra X-ray image, and this is optical image. At the center of the cluster, there is an AGN, NGC 4696. And in the X-ray image, there are some structures here. This is suggesting the AGN feedback in this cluster.
I guess that's Centaurus A.
No, this is not Centaurus A.
Okay. So I recognize NGC number.
Yeah,
So Centaurus plus is not nothing to do with Centaurus.
yes,
Okay.
no relation.
Okay.
This is the field of view of XRISM overlaid on the Chandra image. And for example, we can observe X-ray spectrum like this from this region. And this panel shows a zoom up around 6 kb, 6.5 to 6.7 kb. And this is a characteristic X-rays from helium-like ion. And they are fine structures, and this line is a resonance line. The transition is like this. And the other 3 lines are kind of forbidden lines. And X and Y, here and here, are called intercombination lines, and the transition is like this. And this line is officially called forbidden lines. The transition is here. And as I said, Resolve can observe fine structures from these characteristic X-ray lines. And if we measure the center energy of this resonance line, we can measure the bulk motion of the cluster hot gas, of course, along line of sight. And if we measure the width of this line, we can measure the turbulent velocity. And this is the result. They are the results. This panel shows the bulk velocity, and this panel shows the turbulent velocity. And bulk velocity, the blue means blue shifted relative to NGC 4696, the central AGN. And this figure shows all region is blue. That means the hot gas is blue shifted toward us. And this is the turbulent velocity, and the red is around 150 kilometers per second, and blue is about 40 kilometers per second. And main conclusion is that here is AGN, here is AGN. Around the AGN, we do not observe the large change of bulk velocity or turbulent velocity. So this suggests the AGN does not seem to play a significant role to suppress the cooling flow. Although we see some structures in X-ray image. We can observe this bulk velocity, and we now imagine what the cluster gas, how the cluster gas moves. This is a cartoon of the cluster gas motion XRISM observed from here, and here is the central galaxy NGC 4696, and hot gas is streaming toward us like this, and then moving around the central galaxy like this. This is a cartoon of the cluster gas motion. What is the origin of this gas motion? By measuring the velocity distribution of member galaxies, this cluster consists at least two galaxy groups. This means the small galaxy groups are now merging to form the Centaurus cluster. This is a cartoon of this image. The cluster has not been relaxed yet. And NGC 4649 is oscillating in the gravitational potential well of the cluster center. And this motion can induce the sloshing of gas motion. What is a sloshing? Sloshing is this. You can see the move of the red wine in the grass, and this is a sloshing. And the motion of the red wine, like this, the cluster gas is moving in the potential, gravitational potential of the cluster center. And the cluster gas has a turbulent motion, and that turbulent motion will turn into the heat energy. The turbulent heating rate can be calculated like this. Rho is density, and sigma is turbulent motion, and LT is a characteristic length. And the radiative cooling rate can be calculated like this. Ne is the electron temperature, Np is the ion temperature, ion density, number density, and lambda is a cooling function. And we can observe sigma, L, and Ne and the temperature like this by using XRISM data. And then we can calculate the rate between turbulent heating rate and the cooling rate. The ratio should be almost 1, 0.5 to 1.1. This means the turbulent heating can compensate for the gas cooling, at least currently. And the main source of the turbulence seems to be the gas sloshing, not AGN. This is the main conclusion of the XRISM result of the Centaurus cluster. Okay, do you have any question about this result?
I have a question. So,
sure.
When you measure the bulk velocity and turbulent velocity, did you use the property of the polymeter, something like the F?
Yeah, sure.
I'm sure.
We used all emission lines.
Please show me the spectrum. Yes. So, I thought the bulk velocity can be measured by position, and which can be used to measure the turbulent velocity.
Yeah.
I know that, but I don't know how to use the F and Y and F, Y, and X to deduce something.
Yeah. We have a theoretical plasma emission model, and then it predicts some center energy and width. Then comparing the theoretical prediction and all of these data, we can measure the central energy. Of course, mainly determined by this resonance line, but analysis includes all these emission lines. Okay. Does it make sense? Okay.
So if the sloshing is producing the extra heating to keep the gas hot, then I guess there has to be some estimate for what sort of mass ratio you have to have for the interacting groups to keep the sloshing significant enough to contribute to the energy?
Probably, and I do not remember that mass number, but you can find that mass in the Nature paper, I think.
Okay. But I guess you could imagine a situation where the small galaxies that are coming onto the cluster might be too small to produce enough sloshing to heat that up. And in that case, there must be some other mechanism?
Yeah. And at least we think this gas sloshing will continue not so long. So probably maybe another mechanism, we need another mechanism to suppress the cooling flow perfectly. We do not understand that other mechanisms.
Okay.
But at least now the cooling may be compensated by this gas sloshing motion.
But is it also true for the other clusters?
We are not sure. So we have to observe other cluster galaxies. And many papers will come soon. So stay tuned. I know some results, but I cannot talk today. All right. Okay, let's move to another topic. Sagittarius A East. This is supernova remnant. What is Sagittarius A East? This is the X-ray image of the galactic center. Blue is in X-ray band and red is in radio band. And here is the famous Sagittarius A star, which is a supermassive black hole at the center of the galaxy, Milky Way. And here, the hot gas is here, and this is Sagittarius A East. And in this image, it's not so clear, but in the radio image, we can see shell structures like this for this supernova remnant. And X-ray is filling the center region of the shell. So this supernova remnant is classified as mixed morphology SNR. This means the shell in a radio band and central field morphology in X-ray band. And this is a standard picture of SNR evolution. This is a cartoon. There are two shock fronts here and here. And this is a forward shock front, and this is a back reverse shock front. And this part is interstellar matter or circumstellar matter. And this part is shocked ejector. And this line shows contact discontinuity. And the theoretical calculation shows the density distribution like this. This axis shows the radius, and this axis shows density. And there are two jumps here and here. This is forward shock and reverse shock. Forward shock is here, and reverse shock is here. And this is contact discontinuity. This is just a theoretical calculation. And shock speed is about 1,000 kilometers per second, so very fast. So by shock heating, X-ray emitting plasma is generated by these two shock waves. But the heavy elements contained in this hot gas are being ionized with collision with electrons, but the density is not so high, 1 per square centimeter. So this ionization process is very slow. Then we can define several temperatures. One is electron temperature. KTE is defined like this, just kinetic energy here. And we also can define ionization temperature like this, TZ, which is called TZ. This is kind of a Saha equation, temperature determined by the Saha equation. And if TE equal to TZ, that plasma is in equilibrium. But a few thousand years, NET, density, number density of electron times the age of the plasma. This is called recombining time scale. Is roughly equal to 10 to the 12 is required to reach TE equal TZ. Before the equilibrium, TE should be larger than TZ. electron temperature is larger than the ionization temperature. And this kind of plasma is called ionizing plasma. And since ionization process, ionizing process is now going on inside the SNR. And actually, many SNRs show ionizing plasma. I will show you some example. This is the X-ray spectrum from Tycho SNR. And here is X-ray energy, and here is counting rate. And please take a look at this feature. This is ion characteristic line. And the center energy of characteristic X-rays from ion is like this. If the ion is close to neutral, the center energy is around 6.4 keV. And if ion is ionized to helium-like ion, ion 24 plus, the center energy is about 6.7 keV. And if ion is more ionized to hydrogen-like ion, that means contain only one electron, Fe25 plus, the center energy is close to 7.0 keV. But Tycho SNR shows the ion line at 6.4 keV. This means ion atoms are not ionized, close to neutral. This is the evidence of ionizing plasma in supernova remnants, and actually many SNRs show such line emission. But recently, some strange SNRs have been found. Some mixed morphology SNRs shows electron temperature is less than ionization temperature. This is an example of the W49b, and this actually shows X-ray spectrum, and this is a famous ion line, but please look at here. This is kind of an H-like structure here in X-ray spectrum. This H-like structure can be understood as a free bound emission from helium-like ion. I mean the ion 25 plus hydrogen-like ion collide with electron, and this electron is captured to ion and then emitting free bound emission. And this signature can be understood as this free bound emission. This means the ionization temperature is larger than the electron temperature. In other words, the ions are ionized, highly ionized compared to the electron temperature. This kind of plasma is called over-ionized plasma or recombining plasma. Some mixed morphology SNRs show this peculiar structure. We do not know the mechanism producing this over-ionizing, but anyway, several SNRs show this kind of structure. What about Sagittarius A East? There are two papers. One paper found a signature of the free bound emission from helium-like ion in the Suzaku spectrum. So they claimed the plasma in Sagittarius A East is over-ionized. But the other paper said there are no strong evidence in the Chandra spectrum. So they claim the plasma is not over-ionized. So the plasma status of Sagittarius A East is not clarified yet. Therefore, we observed Sagittarius A East. This is an extend image overlaid the microcalorimeter field of view, Resolve field of view here, and the magenta shows the Sagittarius A East. And unfortunately or luckily, there are some transient source in the field of view here. This is X-ray binary suddenly coming up. But fortunately, this source, the spectrum of this source is only the continuum has continuum component, no emission lines. So of course we take into the effect of the contamination from this source in the X-ray spectrum analysis, but the emission line mainly coming from Sagittarius A East. This is a spectrum of Sagittarius A East. This axis shows the X-ray energy, and this axis shows counting rate. And here is a famous emission lines from helium-like ion. And we can also observe the emission lines from hydrogen-like ion. Here is Lyman alpha 1, and here is Lyman alpha 2. We can observe the fine structures here. But let's take a look at these emission lines. Let's compare this spectrum with a spectrum from Centaurus cluster. This panel shows a Centaurus cluster spectrum. This panel shows a spectrum of Sagittarius A East. As you can easily see, the forbidden line is stronger than the resonance line. In the case of Centaurus cluster, of course, the resonance line is the strongest. Why? The forbidden line, or X and Y lines, are comparable to W resonance line. This is a typical spectrum of from the plasma in collisional ionization equilibrium. And this is an energy diagram of fine structures. And in the case of the collisional equilibrium plasma, the excitation always starts from the ground state here. And then by the electron impact, the electron here is popping up to the higher levels. And the excitation rate of the resonance line here, this level, is the highest one, because this is the electric dipole transition. So mainly this level is populated, and of course transition rate from here to here, the A coefficient is the highest here. So the resonance line is the strongest one in the case of collisional equilibrium plasma. But if in the case of overionized plasma, a free electron is captured to a higher energy levels, the principal quantum number is larger than 3. And then the electron cascades into this level, n equal 2 levels. Therefore, those n equal 2 levels are populated equally. Therefore, X, Y, and Z, the strength of these lines is comparable to the resonance line. Therefore, the strong forbidden X and Y lines are direct evidence of overionized plasma in Sagittarius A East. And of course, we can compare the results with theoretical model. This is a theoretical model of collisional ionization equilibrium plasma. And this axis shows the Z over W ratio. And the observed ratio is here, shown in red band. And this is a theoretical model. And this axis shows the electron temperature. And as you can see, the CRE model cannot reproduce the line-strong ratio between Z and W. As I said, we can measure the emission from hydrogen-like ion, and this axis shows the electron temperature, and this axis shows the present ionization temperature. And from the Z over W ratio, Z and W ratio, we can obtain the region like here, shown in red. And from this ratio between Lyman alpha emission lines and this resonance line, lambda alpha over W ratio, we can obtain these regions, this region shown in blue, and then we can obtain the temperature, electron temperature is like 1.6 keV, and the present ionization temperature is about 5 keV. This is a this is a result obtained by XRISM X-ray microcalorimeter, and this is a current ionization temperature. So the initial ionization temperature must be higher than this value. So this must be higher than 4 keV. So let's compare this data with theoretical model and non-equilibrium recombining collisional plasma model we have. This is so-called RNEI. The parameters of this model is electron temperature and the initial ionization temperature and recombination time scale, NET. And what an RNEI model calculates is put ions with T init into the sea of electron with TE and see what will happen to the ionization temperature as time goes. This is what the model calculates. And this axis shows the recombination time scale NET, and this axis shows the ratio Z over W, and this axis shows the lambda alpha over W, and the red one is observed values. And this axis shows the recombining time scale, and this axis shows the initial ionization temperature, and here we obtain these regions shown in red. This panel shows the recombination time scale must be less than 8 times 10 to the 11. And some parameters can reproduce the Z over W ratio and lambda alpha over W ratio, like here, like here. What is the plasma age? And from the X-ray luminosity, we can obtain the density of the electron. That is about 10 per square centimeter. And plasma age, therefore, from here, NET should be less than 8 times 10 to the 11. So we can guess the plasma age is less than 2,500 years, like this. But note that the uncertainty is very large. This is kind of an upper limit. So what is the origin of the overionized plasma of Sagittarius A star? Maybe this is the past activity of the supermassive black hole Sagittarius A star. And stroke X-ray flare can ionize plasma, keeping the electron temperature constant, and can realize TE is smaller than TZ. To make the ionization temperature of 5 keV, the luminosity, ionizing luminosity must be larger than 10 to the 41st erg per second. But of course, now Sagittarius A star is not bright X-ray source, but some papers claim that Sagittarius A star got outbursted in the past. A few years ago, the ionizing luminosity is kind of 10 to the 39 erg per second, and some 10 to the 5 or 10 to the million years ago, the luminosity should be 10 to the 44 erg per second. So this level of luminosity might be the Sagittarius A star might have flaring activity of this level in the past. This is a speculation, but maybe the origin of Sagittarius A star is the origin of the overionized plasma. Okay. So this is preliminary results. Maybe come out soon. in some famous paper. So, but this is, keep it a secret, please, and do not take photo or do not take more memo about that.
But the video is.
Oh, really?
This,
Video tape. Okay, but keep it inside. Okay.
maybe I can tell to Lauren to.
But of course, you can enjoy this result, but do not tell it to other people. Please, I will be punished. Okay.